Our next chapter, ordinary differential equation. A differential equation is an equation involving at least one differential coefficient without the variables from which these differential coefficients are derived. Here we are on the whiteboard. There are 7 differential equations we have to see. So to define order and degree of the differential equation, the order of the differential equation is the order of the highest derivative of the equation. Highest derivative of the equation here. Highest derivative is 1, 1, 2, 3, 1 and so on. So thus equations 1, 2 and 5 are of first order. 1, 2 and 5 are of first order since highest derivative is 1 in these 3 equations. 3 is of second order. Highest derivative is 2. 3 is of second order. And 4 is of the third order. Since the highest derivative is 3, this is third order. This is of third order. The degree of an algebraic differential equation is the degree of the derivative of the highest order in the equation after the equation is freed from radicals and fractions in its derivative. Strictly speaking, the term degree is used with reference to those differential equations only which can be written as polynomials in derivatives. So consider here the differential equation, say 4. So if we want to proceed to make it freed from radical and fraction, so taking the fourth equation here, cubing both sides, we get cubing both sides. What we get? Cubing both sides we get here 1 plus dy dx whole square, that equals to dy dx whole square whole to the power 2 equals to d cube y dx square, d cube y dx cube whole to the power 3. So now the equation 4 is freed from radical and fraction. Then what happens? So first of all, what we done here, first of all we consider the given differential equation which is freed from radicals and fractions in its derivative, so that we have to cube both sides and proceed further. And the equation, this equation is of the highest order. Highest derivative is d cube y dx cube. This is the highest derivative, which is of third order. Show that. And the index of the highest derivative is 3. Index of the, this is the index of the highest derivative is 3. So 3 is the degree of the differential equation also. Therefore the order of the given differential equation, order and degree of the given differential equation is 3 and 3. Order and degree, this is of third order derivative, and degree is index of this highest order. And if we consider these type of problems belonging to the short questioning part, short answer type part, that is problem 1, find the differential equation of all straight lines passing through the origin. The differential, we have to find the differential equation of the all straight lines passing through the origin. We know that let the equation of all straight lines passing through the origin can be defined as in this way: y equals to mx. So if we substitute different values of m, we get different straight lines passing through origin. So first of all, if we differentiate it with respect to x, differentiating with respect to x, what we get? we get simply dy dx equals to m, which is constant, m into 1. So if we take this equation as 1 and substitute the value of m equals to dy dx and put here, we get y equals to dy dx into x, so that finally after simplification we get x dy minus y dx equals to 0, which denotes the required differential. This denotes the required differential equation of all straight lines passing through origin, of all straight lines passing through origin. This is the first problem. Nextly, if we consider the second, show that b equals to a by r plus b is a solution of the differential equation. This should consider the given equation first. b equals to a by r plus b, If we differentiate it with respect to r, we get differentiating with respect to r, we get what we get? dv dr, left hand side, equals to a is constant, 1 by r, differentiation of 1 by r with respect to r is minus 1 by r square, plus b constant, so derivative of a constant is 0, so that we get this, and finally we get it as a equals to minus r square into dv dr. This is a. So consider it is minus a by r square, which is our relation 2. This is our, say, relation 1. And again if we differentiate, again differentiating with respect to differentiating what? Again differentiating y2 with respect to r, we get what? d2v dr square, that equals to d2v dr square. Here minus a is constant, differentiation of 1 by r square with respect to r, which is minus 2 by r cube, and accordingly we get a into 2 by r cube, and from here the value of a can be expressed as minus r square into dv dr into 2 by r cube. So what happens here? So this is after simplification, minus 2 by r into dv dr, minus 2 by r into dv dr. So if we arrange, finally we get the result as d2v dr square plus 2 by r into dv dr equals to 0. So we consider the fact that we start from the given expression and finally we reach in this relation, so which proves that this one is the solution of the differential equation d2v dr square plus 2 by r dv dr equals to 0.